Okay, today we are discussing about the another combination circuit which is the full subtractor. Okay, and this is the block diagramic representation of the full subtractor, and it have the three inputs and it have the two outputs, and the inputs are labeled as A, B, and the third input is the borrow in. Okay, and which can also be written it as the C. Okay, instead of B in, here I am writing it as the C. Okay, the full subtractor inputs are the A, B, C, and the output of the full subtractor are one is the difference, next one is the borrow. Just for easy accessing purpose, I am redefining it as the difference, I am representing it as the D, and borrow I am representing it as the B. And this is the truth table for the full subtractor, and these three are the inputs for the full subtractor, and these two are the outputs of the full subtractor. You just follow the similar procedure what I explained in the half factor design procedure, and based on that procedure you just try to fill this truth table for the full subtractor. Anyhow, I will explain the how we get difference column and borrow column for one input combination, and that input combination is A is equal to 1, B is equal to 1, and C is equal to 1. Okay, first you subtract these two. 1 minus 1, subtraction is 1 minus 1, difference is 0, you write difference here. So for this subtraction, is there any borrow required? Not required. You put a borrow as 0. Okay, next this difference is the 0. Next one is the 0 minus 1. 0 minus 1, subtraction is possible? Not possible. Then you take a borrow. That's why you make the borrow equal to 1. Okay. So previous difference is 0. 0 minus 1. Subtraction is not possible. That's why you take a borrow. This borrow is 1, means this borrow equal to 1. Next, what is the difference between 0 and 1? Difference is 1. That's why in the difference column, here you write it as the 1. Okay, in this fashion you just try to fill the truth table for the full subtractor. Once the construction of once you constructed this full subtractor truth table, and from this truth table and you go through the output columns. Okay, one output column is the difference, next output column is the borrow. In the output column, wherever ones are present, consider those input combination and try to express those input combination in the algebraic form, and try to put in the minterm form. Then it becomes the D is equal to sigma m of 1, 2, 4, 7. So here this is 1. Okay, go to the corresponding input combination. This is A bar, B bar, C. A bar, B bar, C. Its equivalent decimal value is the 1. In min term, in short form, we are writing it as the M1. We are writing it as the M1. In the same way, try to write it in the min terms form. Okay, the difference equation is D is equal to sigma m of 1, 2, 4, 7. In the same way, you just try to fill the Boolean expression for the second output of the full subtractor, which is the borrow, which is equal to sigma m of 1, 2, 3, 7. Okay, once in our hand the Boolean expressions are present, you just try to simplify the Boolean expression to the possible extent. So here I am simplifying the Boolean expressions using the K-map, and here which K-map is suitable, and that is to be decided by your block diagram, your block. So here my block is the full subtractor which have the three inputs. That's why you take the three variable K-map, and this K-map is for the simplification of the Boolean expression for the difference. Okay, and enter the corresponding minterm. You just map the minterms into the three variable K-map. So here the minterms are 1, 2, 4, 7, and these are the respective positions of 1, 2, 4, 7. After mapping the minterms into the three variable K-map, okay, we can say that there is no adjacent minterms. Once there is no adjacent minterms, the grouping is not possible. You just try to write all the minterms corresponding algebraic equations as it is. Okay, this minterm corresponding algebraic expression is A bar, B bar, C, and this minterm corresponding algebraic expression is the A bar, B, C bar, and this minterm corresponding algebraic expression is the A, B bar, C, this one, and this minterm corresponding algebraic expression is the A, B, C. Okay, so here I am simplifying. Okay, I am re-expressing this Boolean expression in a convenient way as you just consider the first minterm and the last min term. Okay, in these two a bar is common, the remaining terms are b bar c plus next one is the bc bar. Okay, and come to the second min term and third min term. In these two, which literal is common? A is common. The remaining part is bc plus b bar c bar. Let us assume this is x. Once this is x, this is the x bar. Why? Because here what is x? B bar c plus bc bar. Okay, this is nothing but the b xr c. And what is this? bc plus b bar c bar. And this is nothing but the b xnr c. What is the relation between the xr and xnr? Both are complement to each other, and based on that I am writing this as the x, and this becomes the x bar. Therefore a bar into x plus a into x bar. Okay, you just as per the XOR gate output, so this is nothing but the a XOR x, which is equal to, so which part we consider as the x? This part is nothing but the b XOR c. Therefore the simplified, this is not the simplified Boolean expression, so here the simplification is not possible, but we rewritten this Boolean expression in a convenient way as d is equal to a XOR b XOR c. In the same way, you just follow the same procedure to simplify the borrow Boolean expression, which is equal to sigma m of 1, 2, 3, 7. You just map all the minterms into the K map and group the minterms. So here 3 groupings are possible. Okay, and from these grouping, the simplified minterms are a bar b plus bc plus ca bar. So therefore the simplified Boolean expression for the difference and borrow of the full subtractor are, one is d is equal to a XOR b XOR c, and borrow is equal to a bar b plus bc plus